we have the problem. A sphere radius 5 centimeters and a cone of base radius 5 centimeters and height 10 centimeters rests on a horizontal table surface. A horizontal plane 3 centimeters above the surface cuts both solids. As you can see, I've drawn an illustration here to illustrate the situation. Basically, I've drawn an edge view of the sphere, a globe or a ball, and a cone sitting on top of a table. The cutting plane is perfectly parallel to the table and cuts these two figures 3 centimeters above the table. So A, find the radius of the circular cross-section of both the sphere and the cone. There is a known geometric principle that if two chords intersect within a circle, the product of the lengths of the segments of one chord equals the product of the lengths of the segments of the other. Thus, the length of segment GK times the length of segment KH equals the length of segment LK times the length of segment KF for the circle. Diameter LF, as you can see, is drawn perpendicular to the table and the cutting plane. Therefore, LF is perpendicular to GH. And it is also a known geometric principle that a perpendicular bisector of a chord passes through the center of a circle. Since LH passes through the center of the circle and is perpendicular to chord GH, it must be a perpendicular bisector of chord GH. Thus, segment GK equals KH. Let's call this length X. So GK equals KH equals X. And we have, and note, that X is the radius of the circular cross-section created by the cutting plane. This is the quantity we are trying to solve for in the sphere. So we have that X times X, or X squared, equals 7 times 3, which is LK times KF, which is 21. So X equals the square root of 21 centimeters, which is as simplified as we could get, since 21 is the sum of two prime numbers, the product of two prime numbers. For the cone, we have triangle ABC is similar to ADC, since the cut DE is parallel to BC. It creates two similar triangles. Since the triangles are similar, corresponding parts are proportional. Thus, DM divided by AM equals BN divided by AN. That is, DM is to AN as BN is to AN. And note, DM is the quantity we are looking for in the cone. So we have DM equals BN times AM over AN, and all we've done here is multiply both sides by AM. And plugging in the numbers, we have 5 times the quantity 10 minus 3 all over 10. 10 minus 3 is 7, times 5 is 35, divided by 10 is 3.5 centimeters. Okay, part B. Assume the small circle is the equator of a globe. Well, in here I'm not given it a picture, and so I am going to assume that the small circle is the equator of a globe. And a globe is a sphere, a solid sphere. Now draw a diameter for this circle, that is the circle that is the equator around this globe, through the very center of this globe, through the very center of the earth, so to speak, if the globe were the earth. This diameter that we've drawn through the center of the globe, through the circle of the equator, represents AB in the given problem. It says if points A and B are the endpoints of a diameter of the small circle, so consider the equator the small circle, a diameter through the center of the globe, and A and B are both on the circle and points on the diameter. Okay, so note that A and B are now on the opposite sides of the globe and are on the equator. But since the globe is solid, if we want to travel from A to B, we must travel over or under the globe. This is what a great circle path is. Now, a great circle path is a semicircular path from one point to another, or a circular arc where the circle it's a piece of also goes through the center of the globe. So if we cut any arbitrary cross-section through the center of the globe, say perpendicular to the equator, we will see A and B on each side of the circle, and we'll see that we have to take a half circle path over the top of the globe or a half circle path under the bottom of the globe to travel from A to B, because we cannot travel through the solid. So therefore, to go from A to B, we take a semicircle over the top of the globe. There are actually very many such equivalent paths, all semicircles, with a distance of the whole circumference of the Earth is pi times the diameter, or the globe. So it's a semicircle, 1/2 of this. So the distance is 1/2 the circumference of the globe equals 1/2 times pi times the diameter of the small circle. So the answer for B is pi over 2 times the diameter of the small circle, whatever that is. We're not given it in B. And that's it. Thank you.